This is the fourth video in the gas law chapter, and in this one, we're going to now talk about pressure and temperature. So we have a diagram over here, and my arrows represent pressure, and you'll notice that my volume is staying the same. So we're talking about what happens if we increase pressure to temperature. So you'll notice that we get more of these little red dots and more of these little red arrows. These red arrows represent molecular movement. So we get the arrows are molecular movement. And remember, we said back in the first video that temperature is a measure, temp is a function of kinetic energy. I'm going to abbreviate that KE. So what we see here is we get more kinetic energy. As we increase the pressure, we get more kinetic energy amongst the molecules and atoms. Well, if I have more energy, I have more temperature. So these are directly proportional. So that means that temp is directly proportional to kinetic energy. So what this tells me is as pressure goes up, temperature goes up. So we can say that these two are directly proportional. Directly proportional. And if we were going to write this into an equation, we would say P equals a constant times temperature. So because they're on opposite sides of the equation, we know that they're directly proportional. Now, this isn't very helpful, though, if we're talking about changes. So if we rewrite this, we can do P1 over T1 equals P2 over T2. I'm going to put an asterisk here because temperature, temp, it's an M. Temp is in Kelvin. Temperature must be in Kelvin. And the guy, there's actually two guys that figured out. One's last name was Gay, one's last name was Lussac. So this is called GayLussac's law. Now this is very similar to Charles' law, except we had V1 over T1 equals V2 over T2. Because this is so similar, I don't have any practice problems on this page because it's just like what we did with Charles's law. But we do want a mnemonic. So how do we remember that Gay-Lussac's law is direct proportionality between pressure and temperature? Well, we could say we can abbreviate Gay-Lussac's name to GL. And back in the day, there used to be people that went door to door and would sell things, and we called those door-to-door salesmen, and they would do direct sales. So direct sales is from one person to another. So let's say that GL is in direct sales, and what's he going to sell? It has the letters P and T. Well, you guessed it, toilet paper. So GL directly sells toilet paper, or TP. So that tells us that Gay-Lussac's law is a direct relationship between pressure and temperature. All right, the other thing we're going to talk about today is the combined gas law. So we're going to take Gay-Lussac's law, Charles's law, and Boyle's law and bring them all together. And when we do, it looks like this. P1 V1 over T1 equals P2 V2 over T2. So if you have all three variables, you can actually, you don't have to calculate each one individually. You can use this combined gas law. And because this is similar to what we've done before, I'm just going to jump right into calculations. So our first problem is a diver blows, let me go, I'm going to rewrite this. This problem was modified. I don't have the modified version. So in your version, it says a diver blows a 0.75 liter air bubble underwater. As it rises to the surface, the pressure goes from 2.25 atmospheres to 1.03 atmospheres, and the temp goes from 20 degrees to 25 degrees Celsius. From 20 degrees Celsius to 25 degrees Celsius. what will be the volume of the air in the bubble at the surface? Well, we're going to do a variable bank again, except this time I'm going to have P1, V1, T1, P2, T2, V2. Okay, so we start off with 0.75 liters in our volume. And my temp one, I need to put that into Kelvin. So that's going to be 293. My pressure, the pressure goes from 2.25 atmospheres to 1.03 atmospheres. T2 is going to be 298. If I put that into Kelvin, and we're solving for V2. So when I plug my numbers in, I get 2.25 times 0.75 over 293 equals 1.03 times V2 over 298. Now, just to be clear, you're still going to cross multiply, so your linear equation is going to be 298 times 2.25 times 0.75. And remember, I can have the pressure in atmospheres or kilopascals as long as it matches both sides of the equation. And then on this side, I'm going to have 293 times 1.03 times V2. I didn't pre-solve these, I should have. So let me do that now. 295 times 2.25 times 0.75. I'm going to divide that by 293 times 1.03. And I get 1.66. I'll round that to 1.7. V2 is 1.7 liters. And let's see if that makes sense. So my volume went up. Well, my pressure, my temperature went up, and we know that volume and temperature are directly proportional. So if temperature goes up, volume should go up. Okay, check there. My pressure went down, 2.25 down to 1.03, and I know that volume and pressure are inversely proportional. So yes, this answer makes sense. All right, go ahead and pause the video and try this second one, and I'll see you in a minute. Okay, let's see how you did. So again, we've got our P1, V1, T1, P2, V2, T2. And when I convert these, my 30 degrees is 303 and my 80 is 353. So now this time my pressure's in kilopascals, and that's okay. So here I have my first pressure is 110 kilopascals. My volume is 2 liters and my temperature is 303 Kelvin. My temperature goes up to 353 Kelvin and my pressure goes up to 440 kilopascals. And they want me to solve for V2. So I'm going to have 110 times 2 divided by 303 equals 440 times V2 over 353. When I write this out long form, I'm going to have 353 times 110 times 2 on this side. And on the other side, I'm going to have 303 times 440 times V2. So in this one, again, I kind of have the same parameters where my temperature is going up and my pressure is going, where's my pressure? My pressure is going up. So we're not quite sure in this one because we have multiple changes. So we've got 353 times 110 times 2. I'm going to divide that by 303 times 440. And I get 0.58 or 0.6 V2. Let me punch that in again. 353 times 110 times 2 divided by 303 times 440. And I get 0.58 V2 equals 0.58 liters. So even though my temperature went up, I had a pretty big pressure increase. And we know pressure and volume are inversely proportional. So the pressure kind of outweighed the temperature. And I end up with a smaller volume. Okay, that is it for combined gas law. It's our takeaway. We talked about Gay-Lussac. That's a direct relationship between temperature and pressure. So we get P1 over T1 equals P2 over T2. Then we talked about combined gas law and did a couple sample problems with that. Okay, the last video in the next video is the ideal gas law. That's it for now.